Okay, I think we can get started. You ready? Okay, we're
Okay.
very happy to have Albert Law here from Stanford, talking to us about horizon scattering, partition functions, and hedge funds.
Hi everyone. So first of all, thank you for the invitation. It's a great pleasure to be here. So this talk will be based on a couple of papers, especially these two, with Montreal Group and Klaus Parmentier, who are grad students at Columbia University. And then and then partially will be based on some upcoming work with Adam Ball and Gabriel Wong, both are postdocs, one at Parameter Institute and the other one at Oxford. And
Where's Ninos and Denef? Where are they?
Dio is at King's College London right now,
King's College.
and Frederick is at Columbia.
Denef is in Columbia.
Yeah, thank you. And all of these are, were inspired by this earlier paper with them and Zimo-san. So to start with, to motivate what I'm going to say later in the talk, I'll just remind everyone a proposal by Gibbons and Hawking almost 50 years ago. So the assertion is that thermal canonical partition function for black hole thermodynamics is computed by a Euclidean path. The idea is very simple. Just let me remind everyone, in quantum field theory, on a space-time, in this product form, some space times time at some finite temperature, an object of interest is a thermal canonical partition function like this. First of all, of course, this thing can be computed in a standard ways, like you quantize your theory, construct a Hilbert space, and then you actually compute the trace by summing over all states, right? But the other way of computing this quantity is to interpret, is to first of all think of that you have an amplitude from some field configuration to some other field configuration connected by some Euclidean time evolution. Okay, and then the trace is implemented by identifying the field profile at the Euclidean time zero and Euclidean time beta, and then you identify them and then integrate them over. Right? So ultimately, you have a path integral on a cylinder like this with the formal circle. So the path partition function is equal to a path integral periodic in Euclidean time. Right? Okay. And what Gibbons Hawking said was that, this should remain true in quantum gravity. And to be more precise, the object of interest is this gravitational path integrals. Here, we integrate over all Euclidean metrics and matter fields periodic in Euclidean time, right? Of course, actually, if you think more about this guy, it's not even, completely well defined, right? But operationally, what we usually do is we just expand around some saddle points, and then we integrate the fluctuations around that saddle point. Okay. So operationally, this is what we do. Okay. But of course, even at that level, it's still not clear, right? Precisely, okay, what we're doing, right? For example, what are we summing over? Okay, and also, some of us might know, there's a well-known conformal factor problem. In the gravity sector, the trace mode will make the action actually unbounded from below. Then, even though Hawking said, we should do some analytic with rotation in field space and make the thing well defined. Anyway, so we're interested in this object. And Gibbons Hawking said that such a path integral should compute some thermal canonical partition function, just in the case of QFT. Okay. For black holes, the Euclidean black hole geometries, they arise as saddle points for the Einstein-Hilbert action, right? And the tree at tree level, right? This indeed yield the expected result. Okay. So yeah, so well, people got convinced by that, and then okay, and in fact, in some cases, it agrees with microscopic black hole entropy calculated from string theory, including some corrections even. Okay.
When is it that higher derivatives corrections do not affect this result, and when is it that they do?
They do.
But here you say exact agreement. You say including higher derivative corrections.
Oh yeah, well, also if you have higher derivative correction, right, the higher derivative correction will change, right?
That expression.
Yeah.
I misunderstood the statement there.
Yeah, sorry about that. Yeah, but
there will be some formula, but there will be corrections.
Yeah, there will be corrections. For example, even the tree level will be corrected.
Okay.
Okay. But okay, going back to the question, right? We never actually have a derivation for the polynomial in the first place, okay, from the Hamiltonian formula, right? For the QFT case, we do, but in the gravity case, we don't. We just took that polynomial as a sort of a generalization, for what we did in QFT, but we never actually have a derivation for the Euclidean polynomial. So what are we actually doing? So this talk will focus. Well, I'm not going to answer that question, to full generality today, but today we'll focus on the one loop part, which comes from quadratic fluctuations around Euclidean black hole background. So that means, this it is really like studying free quantum fields on a fixed black hole background. Okay, yeah, hopefully I'll be able to convince you guys, at least at one loop, what these objects are really about. Okay. So the plan of this talk is the following. First, I'll describe more precisely the setup of, yes.
So when you say there is no derivation of it for the gravity, I mean, people, do they just based on rough arguments, or
I think yes. Right. It is definitely not at this precision, right? In QFT we do, right? We do the usual, Feynman argument. We insert some states and then, right, everything we integrate momentum and then we get some popping rule. But in gravity we never had that.
and still no answer for that.
I don't. But it yields good results, so people have been using it.
Yeah, okay.
Let's call it a conjecture then.
Yeah. I will. Yes.
You mean even A over 4 is not is a conjecture? Is this proven?
No. What I'm saying is, okay, the interpretation of this guy as computing some thermocanonical partition function, right, is a prescription, right? We have been using it for almost 50 years. And it's at least at tree level, is consistent with what we expect from thermodynamics. So that's why I say. But we never have a complete derivation for that object. And actually, we'll see as we review even at one loop, right, for free fields on a black hole background. If you really try to think of the one loop popping growth as some canonical partition function, you run into some issue. So the plan of the talk is, first of all, I will be more precise for the problem, and then I will invoke some and then I will describe in more detail how to make sense of everything in the Lorentzian signature, and then how to connect it to the Euclidean signature, and then I'll talk about some generalization to spinning fields, and then I'll conclude some remarks. So to be more precise, today we'll just focus on a specific setup. We focus on D plus one-dimensional static spherically symmetric backgrounds. It's just simplest but non-trivial background. Okay, and as we all know, if this factor is 0, we have a horizon. Okay, And at that horizon, there is an associated Hawking temperature. And we will consider a case where a temperature is not zero. So not extreme mode black holes. Okay. And then if we do this rig rotation, and then identify the time, in the Euclidean signature, with some periodicity. Well, actually at a specific temperature, the Hawking temperature, then the geometry is you have a smooth Euclidean geometry, right, that arises at a certain point in the Euclidean gravitational path integral. Okay. So in terms of pictures, so the situation is typically like this, right? So you have some outside horizon region with some time, okay. And in this talk, we will do everything beyond the horizon. And there is some, and asymptotic, it really depends on which specific space-time you're talking about. And if you do this rotation and identification, then the horizon will be mapped to this Euclidean origin, which is actually a codimension 2 sphere. Okay. But yeah, unlike the case of you have space and time, here the time cycle is actually contractible. Okay. So now the object of interest is this one loop Euclidean path integral. For example, if you consider free fields, okay, the one loop contribution to the path integral comes from, for example, a scalar is the function determinant like this. Okay, and by this I really mean, right, you have a multiply over all the eigenfunctions of the Laplacian in the Euclidean signature. Okay. Of course, this guy is UV divergent. You need to do regularization, zeta function, heat kernel, for example. Okay. So the question we are going to address is what is a Lorentzian calculation that we produce the one loop determinant that I wrote earlier. And yeah, first of all, okay, again, right, it's like intuition from usual QFT at finite temperature, right? Because the path integral is periodic in Euclidean time, then we might, think that the one loop determinant is computing some trace e to minus beta h at the black hole temperature, right? For some Hamiltonian, okay. Here the Hamiltonian, it's like in the Lorentz signature generate the time outside horizon, right?
Is this the Hamiltonian you obtained from Hilbert-Einstein gravity coupled to a scalar?
No, here I'm just thinking about free fields on background. So yeah, we sort of working at approximation gravity effects. Yeah.
You have a single scalar field in a fixed background. Is that fixed background the black hole?
Yeah.
Okay.
Yeah. Here, for example, an example is a scalar or a static BTC black hole, right? So here, for example, the time, right, generate the time here, right? And yeah, so here we want to think of this h, right, as a Hamiltonian generating this time. And here I'm just drawing the picture for Euclidean BTC, which is really just a solid torus, right? But here we are interpreting, right, this cycle as a time cycle. Right. So okay, let's try to examine this calculation and see if we can actually reproduce a one loop determinant. Let's say, okay, if the spectrum of the Hamiltonian were discrete, okay, we can do the standard exercise in statistical mechanics. We can more expand the fields and then construct a Hamiltonian, and then we construct a Fock space, right? And then we can actually compute a trace, okay, like this. So here, this factor, so here E labels single particle normal mode spectrum. And this factor comes from the 0-point energy for each normal mode. And here, this factor is really just a Bose-Einstein factor, right? For fermions, it will be, it will be in the numerator with a plus, okay? Equivalently, I can just, rewrite this formula in this form. Okay. Here, I'm just rewriting everything in terms of this single particle density of states, right? which is really a sum over data functions. Yeah. Oh, but the problem. Oh, sorry. Oh, yeah. But the problem is the Hamiltonian actually has a continuous spectrum in this case because you have a horizon. Any energies are allowed, right? Because of the infinite redshift. Consequently, the expressions that I wrote down in the previous slide just doesn't make any sense, right? You have any, all the summed over energies, they just completely fail, right?
Are you summing over multi-particle states here?
Single particle, single particle.
Single particle.
Yeah. Yeah, here is sort of like a first quantized approach, right? Because we have a free field, so yeah. But of course, for interacting theories, I don't have much to say today. But here, at least for free fields, we can make. In particular, in the previous slides, right, this density of state actually is infinite, right, for any omega, because we have a continuum of modes, right? For any window of energy, you have infinitely many modes. So this guy is just infinite for any omega, making the trace just completely ill-defined, right? And therefore, this proposed relation just cannot be true, right? Yeah, because this guy is completely ill-defined in the first place. Right. So what's going on, right?
When you say ill-defined, is it divergent?
Yeah, but it's different from the usual UV divergent because it happens for any omega. Right? It is because of the continuum of modes. It's not due to a specific limit of omega.
You cannot also give any meaning to that product, right? I mean,
yeah, just completely it doesn't make sense at all. Okay. So yeah, what's going on? Yeah, the goal of this talk, okay, more precise, is to make sense of what I just described. Okay, how to how to do anything. Okay, and how the sort of modified calculation I described will be related to the path integral and the generalization to spinning fields. Okay, if I have enough time. Yeah, but because you will get technical very soon, very quickly. Let me just state the result and then I will explain everything later. What we will see is that first of all, there is a result number one. Result number one is that here. Well, let me remind everyone. Quasi-normal modes. They are this first column is wrong. So our quasi-normal modes satisfy two sets of bound conditions. First of all, in the context of asymptotic ADS black holes is actually satisfy the standard bound condition where it falls off at spatial infinity. Here, here there is a typo. It's not origin, it's at the infinity. And secondly, it satisfies purely ingoing bound condition at the horizon. Okay, because of the two bound conditions, we actually have a discrete spectrum instead of.
You say outgoing there, but you mean sort of outgoing from the bulk into the horizon. Is that
so?
You said outgoing.
Point. Oh yeah, outgoing. Outgoing. Yeah, I was.
You mean ingoing, don't you? You said ingoing, and then you. I mean,
saying
it can be very confusing. Yeah. It's approaching the horizon. It's approaching the horizon. Yeah, because sorry. Yeah, because as I typed this, I was actually having this in mind. So you would get flipped, right? Ingoing be some outgoing. So okay, but yes, ingoing. Okay, approaching the horizon. Right. Or maybe a better definition is they are poles of the retarded green function. Okay, I guess that's the better definition.
Is this the same as an unroot boundary condition?
Unroot boundary condition. Black hole. Is it exactly the same? No, but I'm not sure.
What do you demand then in these two items you've written? What do you demand happening at the origin? You want the solution to be finite, I suppose. Is that
to be
regular? And at the boundary, what do you want it to be?
Yeah, maybe
at the horizon, in other words.
Yeah. So okay. So first of all, here your demand is vanishing. at spatial infinity is zero at infinity. And the
Okay.
demand, is purely going into the horizon.
What does that mean, purely going to the horizon? Is it finite,
Yeah,
the
sorry.
horizon?
Because near the horizon, the wave equation will be, well, the solution will become a linear combination of plane waves.
Mhm,
You
mhm.
select the linear combination, well, you demand, you don't have the outgoing part.
Mm.
Okay. Anyway,
And regular, finite.
at spatial infinity.
Okay.
I'll write equations down later. So anyway, so quasi-normal modes, okay. And then I define this object that I call, the quasi-normal mode character. I'll explain later what's going on there. But I'll define this object later. And then, and then we'll see that with this guy, okay, we can define some sort of spectral density. Okay. And then with this spectral density, we put this into the formula we saw earlier. Okay. And then, okay, we have some sort of renormalized trace. Okay. And the point is that, okay, this guy turns out will be equal to the one loop determinant. Okay. And then, that's result number one. I'll explain everything. Result number two is that for spinning fields, actually the one loop determinant will has more structure. It will generally be a ratio like this. Okay. First of all, this Z bulk is what I wrote in the previous slide. Okay, and then the Z edge only exists for spin height and or equal to 1, and will be related to quasi-normal modes, satisfying some properties. Okay. Then I will explain. And yeah, let me not say too much here. Anyway, so okay, I'm now gonna explain the result number one. First of all, for concreteness, we'll focus on asymptotically ADS black hole. And for each angular momentum L, right, the Klein-Gordon equation is equivalent to a Schrödinger equation with some potential, right? So here I'm writing the equation of motion in terms of this tortoise coordinate, right, where the spatial infinity is mapped to 0, okay, and then the horizon is pushed to minus infinity. And here, I'm just writing down the explicit form of the potential.
The potential, are you expressing it? Can you go back to the previous slide? On the left hand side, you say that's so you're not changing the coordinate on the right hand side. It's still R.
No, I am. Yeah, these R's are implicitly functions of X. Okay. Yeah. But yeah, let's be I'll write down the V later as an example. Anyway, I don't know why I keep doing this, but all right. So we're interested in normal modes, right? Normal modes, from the point of view of this 1D Schrödinger problem, they are scattering states, right? Okay. And first of all, we will pick first of all, the general solution for the wave equation at infinity generally is a linear combination of going mode and falling mode. Right? And we will pick the standard bound condition, setting this growing mode to 0. Okay. Then that takes out one unique solution to the wave equation. And those are the normal modes we consider. And near horizon, this normal mode is a linear combination of plane waves. Okay. You have some outgoing waves, ingoing waves with some coefficients. So you can really think of, you have some, actually, next slide. So you can think of the problem as you have, the normal solution is like you have some waves coming out of the horizon and going back into the horizon like this. And for the 1D picture, yeah, it's like this, right? This is the plot for the potential that I wrote earlier. So you have some ingoing waves and then bounce out of potential with some outgoing waves. Okay. And it is easy to see that for real omega, the coefficients that complex conjugate of each other. Yeah, you just take the complex conjugate of the solution, it satisfies the same equation. And therefore, this ratio, right, of outgoing coefficients to the ingoing coefficient is a scattering phase, is a phase, it's a pure phase. And in terms of this scattering phase, right, this solution near the horizon takes the form of a cosine. Right. So as I said, right, the problem was, we have a continuum of modes, and then the density of states is blah blah blah, right? And to be more precise, let's put a cutoff, near the horizon. Okay, it's actually like the two brick wall cutoff. Okay, and we just impose some boundary condition at this wall, and it turns out it doesn't really matter what you put here. I'm just putting Dirichlet, for simplicity, right, for concreteness, but it turns out this would not matter. So if you put a cutoff at the wall and then impose some Dirichlet boundary condition, that will mean that, and then you can solve for the spectrum in large R. Then you have some quantization condition like this. Now you have two boundary conditions, so you have a discrete spectrum normal modes.
So do you assume
yes.
that you put boundary condition on the horizon? Basically,
Here is a stretch horizon.
you assume that your phi is 0 on that, or?
You get or some fixed.
But that means that you put a mirror on a black hole.
I mean, you can put Neumann, but for what I'm gonna say later, what you put does not matter. Okay.
Any self-adjoint boundary condition will work.
Yeah.
And give the same result.
Yes.
It's typical of what happens when you move a boundary out to infinity.
Yeah.
Limit point boundary condition instead of a limit circle boundary.
Yeah. We will see more precise. Yeah. Right. Okay. So you can solve. You have a quantization condition in large R. Okay, in this form, and with that, you can write down, a regulated density of states, right? Like this. It's just 1 over the spacing of the normal modes. Okay. It will take this form. Okay. So you see there is a leading term, this wild term, basically proportional to the size of the box. Okay. And then there's a subleading term that depends on the scattering phase. And obviously this guy goes to infinity as R goes to infinity. Okay, you have, this is the problem, right? The ill-definedness of the trace. This is the root of the problem. Okay. However, notice that this leading brick wall term actually knows nothing at all about the scattering potential, right? Okay, as long as you have a scattering problem, with some localized potential, the box has size R, you will have that term. Okay, if you just repeat what I just said earlier, and you have that, divergent term. In contrast, the first subleading term, the term that depends on the scattering phase, actually does depend on, the detail, the shape of the scattering potential. Okay, so this is actually the more meaningful term than the leading term. Okay, and the idea is to find some way to extract this term. Okay, so the strategy we will take is one that employed by actually when this paper was inspired by condensed matter people, and the strategy is the following. Because very often they are interested in differences in free energies and stuff. Okay, so the absolute value does not really matter. So what they would do in that kind of situation is to, compare the original problem with some reference problem. Okay. With some it's like some scattering with some reference, with some potential. Okay. For example, just the minimal, simplest choice, right? Is the scattering problem with no potential. You have a box, then in that case, the scattering phase is a constant, is trivial. Okay. You don't have this term, right? Or you can consider some crazy things like this, right? As long as your scattering potential is localized enough, you'll be good. Okay. And for the reference problem, of course, you can repeat the exercise earlier and then write down some density of states. Okay. The point is that the difference, right, between these density of states, they are completely finite. You can just take out all the way go to infinity. Okay. And then you can define a completely finite good quantity. And here I'm just rewriting everything in terms of the scattering phase. Two comments. First of all, this specific relation here does not depend on the choice of boundary condition at the brick wall. Okay. As long as for the two problems you choose the same thing, okay, you'll be fine. Okay, you have this good relation, and also right, and from the right hand side it's kind of obvious because these scattering phases, they only depends on the asymptotic data, right, for the scattering problem. Okay, and manifestly is independent of the boundary condition. Okay, and ultimately, and take a step back, right? We were considering a specific angular momentum L, right? Ultimately, you need to sum over them, and this will introduce some UV divergence, but we know how to regulate it. Okay. So, and there's here's a connection with polynomial mode. Okay.
Can you remind me again on how did you get the first equation on top?
This equation?
Yeah.
You mean this equality or?
I mean, you get it.
So you have two rows, right? A row and row bar, which takes this form, right? If you take a difference, first of all, this term drops out, right? And the theta, the theta actually will, depend on the s, right? You can rewrite, but theta is basically the s, right? The log of the s.
There's nothing to do with contour integral.
No, okay. So far, no. Yeah, the omega real.
Because you have 2 pi I, so.
Oh yeah. No. That 2 pi I comes from the I come from here. No, and the pi comes from here. And the two, the two come from here. So we have 2 pi. Yes. Yeah, great. Yes. So right, here is a connection with polynomial. So observe that this the row will hit a pole whenever the ingoing coefficient is 0. Okay. We call that this S actually depends on the ingoing coefficient and also outgoing. And the location of these poles, they are precisely the quasi-normal frequencies. Right? If you set the ingoing coefficient at 0, that means you only have waves going into the horizon. And here this comment is because the ingoing coefficient and outgoing coefficient are related, so that means the delta rho must also hit another pole at some other location, just a minus c. And if you take into account all of these poles will contribute to this delta rho in this way. You can just rewrite everything as a integral, right? Sort of a half side Fourier transform of the character, the cosine character I introduced earlier. Okay, So now we're starting to see the connection, right? Yeah. So, yeah, now finally, let's go back to this. So you define calculation. The point is that differences or ratios are better defined than the original thing. And now, if we replace, right, this row with this delta row, right, we can define actually some, a formal difference between free energies or, ratios of partition function, right? For some, as long as we have picked some reference. Okay. So a priori, any reference system, will lead to some well-defined quantity. Yeah, so it seems like, we have an infinite, family of legit answer. Okay. Yeah. But the point is, if you compare what I just said, with the Euclidean path integral, well, because a path integral, is a unique thing, right? You have a number, right? If you compare that with what I just said, the path integral actually picks up a specific reference for you. Okay. And it turns out it's quite interesting. It turns out that somehow the path integral picks out, a non-trivial reference. And the reference here, as I said, here, Wiener is, it picks out the Wiener scattering problem as the reference, okay? Meaning, right now, we have a Wiener-like wedge, okay? And then, again, you consider some free fields on this background, and then you compute the scattering phase, right? For that scattering problem, you will find that the scattering phase for the Wiener problem is a ratio of gamma functions like this. Okay. It turns out if you take that as reference, you will recover the one-loop path integral.
Can I ask you a question?
Yes.
You say that it turns out that that happens. Does it happen uniquely, or did you try many different examples?
Yeah, we try many different examples. I mean, okay, very good. Yeah, so yeah, right. As of today, I still don't have a first principle understanding of why, it picks out the answer. Yeah, but we're pretty sure how that works, because you can compute everything in some examples. We actually computed do this for static BTC, digital static patch, and Naria, any examples you can actually compute everything. Okay. I mean, yes.
But near the horizon, basically physics is just Rinder, so it's not surprising.
Yes, it's not too surprising. But still, we don't have that. We don't have a derivation of this fact. Okay, it's not too surprising. Yeah, I totally agree. But it's for now, it's like oh, we check some examples. Okay, it happens in this nice pattern, but we haven't understood what's going on yet. Right. Yeah. What I'm trying to say. Yeah, anyway, okay, yeah, you can ignore these two lines. Yeah, we actually, compare this Lorentzian calculation with the Euclidean path integral calculation for some examples. And then, yeah, you always pick this out as the answer. So to be a bit more concrete, let's look at, one simple example and see things explicitly. First of all, yeah, we consider, a static BTC background like this. Okay. I don't know why it's keep, skipping 2 slides instead of 1. Anyway, so yeah, if you, in this situation, if you, near horizon, again, anyways, and explicitly, the ingoing outgoing coefficient take this form. So, right, you see this red, vector in red, if you take the ratio of the outgoing ingoing position, this is precisely the scattering phase you get by studying the Wiener problem at the BTC black hole temperature. Okay, and for anyone who has studied quasi-normal modes in BTC before, you'll recognize this factor. It encodes all the quasi-normal modes and anti-quasi-normal modes for BTC. In particular, the poles of this gamma function, they are precisely quasi-normal frequencies. Yes.
Because it came up earlier and again a couple of slides ago. So your notation with in and out.
Yeah. Okay.
In means
Now.
in means out from the horizon into the bulk.
Yeah. Now it's getting even more confusing because in this slide, this in is it's in and out from the point of view of the scattering problem. Okay, so in meaning from the asymptotic from the asymptotic region, and then out is back to the asymptotic region. And the asymptotic region here in this case is the horizon.
Right.
So sorry, it's a bit the in and out. Yes. Yes. Yeah, but here, I'm switching to the point of view to the 1D.
X increases as you go outward from the horizon, right?
Yes.
Right.
Yes.
Okay. And so if the I omega.
Yes. Yeah. Yes. Sorry for
the X. Yeah.
Yes.
Right. Okay.
Good. So you see, the S matrix you define this way, you always, it contains a factor, a Wiener factor. And if you choose, that as a reference, right, you factor that out, and then you define this. So, we normalize spectral density. Okay. Here in this form, just showing, you plot this spectral density if you pick different references. On the left hand side, you pick a sort of minimum reference with zero potential, and then the relative and then you have this bunch of poles. But if you pick the Wiener reference, you don't no longer have those poles. Okay. So, with the spectral density, and the quasi-normal character, just to show you some equations. In this case, you take this form and you plug that back into this formula, you recover what you expect from the Euclidean calculation, on a solid torus. Okay. So as I said, we still don't have a first principle understanding of why the particle pixel, the Wiener reference. But here, let me try to give you some kind of intuition, what's going on. And yes, because near horizon, the space-time actually looks like a Wiener space. And in fact, actually, if you plot the scattering potential for a free scalar on this background, you get this red line. Okay. Where the black line correspond to the original potential. So you see, right, they're really, they're almost like completely overlap, except regions very far from the horizon. And the scattering problem is region reduces to this form with this simple exponential potential. Okay. And you see, imagine we're near horizon, right? Okay. We want to probe the space-time by sending some waves, doing some kind of scattering experiment. Right? We will study this scattering problem. Okay, if you're someone near horizon. Okay. And notice that for this potential, the information of the black hole geometry, except the temperature, right? And the information about the scalar field, that means the mass, angular momentum, everything, becomes completely invisible, right? Because this equation you see, is completely independent of the mass and angular momentum of the scalar. Right? It knows nothing other than the black hole temperature. And yeah, if you solve this scattering problem, you will obtain this S matrix. Okay. Oops. And it's only like if you send your waves far enough, right? So that the waves can detect the non-trivial features of the original spacetime and scalar, they would detect a change, right, in the density of states, right? And the change, is what I wrote earlier. And therefore, they would also detect a change in the free energies. And what we just shown, what I explained earlier, is that the path integral somehow captured that change. Okay, so that's the intuition. So yeah, here is a brief summary. The one loop path integral on Euclidean black hole background should naturally be thought of as a ratio like this. Okay. It's a ratio of binary functions where these traces individually they are not well defined, but ratios of them they are. Here, when I take a ratio, we secretly doing regularization and taking regulator. It's actually some limit. Okay. And in terms of formulas, we can write these into an integral representation of some quasi-normal character. Yeah. So here, I want to make a comment on asymptotically flat black holes. Okay. Just now we've been looking at asymptotic ADS, right? You have a gravitational well at infinity, okay? And the scattering problem is is a half line scattering. Okay. But here asymptotic flat is qualitatively different. First of all, okay, it's actually kind of tricky to think of the black hole plus quantum fields as a system in thermal equilibrium because things can escape to infinity. But in any case, we can just consider the scattering problem and see what's going on. And as I said, because things can escape to infinity. Okay, the scattering problem is actually a two-channel scattering problem, right? The waves can either go from the horizon as earlier or from the spatial infinity, right? So you have two-channel scattering problem. There's some waves, here in the equations. At the horizon, you have linear combination of plane waves, and infinity, you also have a linear combination of plane waves. Okay. Yeah, in terms of pictures, right? Asymptotically flat black holes typically this potential looks something like this. The potential dies off to zero at the horizon and at spatial infinity. And here to define S matrix, you consider the map from ingoing waves to outgoing waves. The map is a scattering matrix. Here I'm writing it in terms of some transmission and reflection coefficients. Right? Like this, and they satisfy these properties. And the analogous relation in this context is this, okay, between the spectral density and the scattering matrix. Okay, here, it's really just the same expression, but with S replaced by the determinant. And it's easy to see that for real omega, this quantity is basically the phase of the transmission coefficient. Okay. And here I'm just trying to make the cute connection with the gray body factor, because the gray body factor is nothing but the magnitude square of the transmission coefficient. Here, I'm just telling you that the phase of the transmission coefficient also contains some interesting information. Okay. Namely, it captures the information about the spectral density. Yeah. So, any questions? Actually,
Sort of 10 minutes.
10 minutes.
A little bit more.
So probably I won't be able to explain everything. But yeah, I'll try to. First of all, okay, yeah, what I just described applied, for scalar. It turns out the stories that actually become more complicated, but actually more interesting for spinning fields. In particular, the first thing, right, the Lorentzian, scattering, blah, 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 those calculations, it extends to spinning fields just straightforwardly. You can just do the same thing. And, and even for spinning fields, it happens that, always, if you pick Wiener as the reference, you can always write down, this sort of renormalized partition function in this form. This is exactly the same formula extended to spinning fields. Okay. However, what's interesting is that for spinning fields, this object is no longer equal to the path integral.
I don't understand. You just said that it does pick out the Lindlar, right?
Yeah. You can always.
That picking out was done by setting these.
If you pick Wiener as a reference,
Yes.
you end up with this expression.
Okay.
Yeah.
But earlier, your criterion for picking out the Lindlar was the
Yes.
fact.
Yeah. But here, that was also scalar. And here for spinning field, we try to do the same thing, which does not reproduce the one determinant. But still, the difference is something, I'll describe. Right. Yeah. So, okay. Here it comes to this, horizon edge function. So, right, based on, it's going to be a very, to completely explain, what ZH is about is a very, very technical argument. I'm not going to, lay out the complete argument here, but, feel free to ask me later. But the argument is, roughly speaking, is based on, analyticity argument, near the Euclidean origin. And that we argue that the path integral for any spinning fields must take this general form. And again, this till z bar is the same thing we wrote earlier. And it turns out this ZH Bernoulli function, is related to a subset of quasi-normal modes. Okay. And I'll try to explain which subset of quasi-normal modes. Okay. So to understand which specific subset of quasi-normal modes will contribute to the difference, we will do the following exercise. We try to quick rotate quasi-normal modes to Euclidean signature. But let me just remind everyone. So in a Lorentz signature, the relevant object is quasi-normal modes. Quasi-normal with some frequency, with some complex frequency, which depends on the mass of the field. And by definition, right, quasi-normal mode satisfies equation of motion, right? With this time dependence, right? And near horizon, it only has, waves purely approaching the horizon. Yes. And on the other hand, in the Euclid's nature, we are looking at completely different things. Namely the eigenfunctions of some Laplacian operator. And here in particular, we're looking at eigenfunctions, with some U1 quantum number K, right? And in particular, near origin, it has this dependence. So what we're gonna do is that we try to vary the m square. Okay. And then we get some mode, and then we, continuing to the Euclid's nature, right? So in particular, we will vary the quasi-normal mode frequency such that it satisfies this relation. Okay, and then you get some mode, right? And then you get some mode, okay, like that. And then we take that, and then we rotate this mode, right? Then you have something Euclidean. So
I in
there is an I. Yes.
in chi k in the Euclidean, you have I called k. Is
Yes.
I is there, yes?
Yeah. Yes. Yeah. So there are two I's, right? So here, IZ, becomes this, but then you also have this quick rotation. So you have two I's. So you are left with one I there. So anyway, so we do this procedure, and then we try to make a quasi-normal mode into an eigenfunction. Right? It turns out for scalars, for all the quasi-normal modes and for all the case, you can always do this, and then you get some good eigenfunctions in the Euclidean nature. But it turns out for spinning fields, it is not always possible. If you take a quasi-normal and do this, do that, you may not end up with a regular eigenfunction of the spinning operator. And ZH is exactly related to those quasi-normal modes that do not rotate to an eigenfunction for some K.
K is taking discrete values.
Yeah, K is integer. K is
Related to
integer.
1 over. Okay.
Yeah, K is integer. Yes. Right. Yeah. Anyway, I didn't explain this statement, but okay. Wow, but I'm just describing the result. So okay, here just to give you an example, just consider a massive vector on static BTC. Which these quasi-normal modes. And here, I'm just writing down the sort of renormalized canonical Boolean function that I wrote earlier in terms of characters and stuff. Okay. And then you end up with something, right, which is not equal to the solar torus result. It is not. Okay. And one, we actually explicitly checked that the quasi-normal modes with this, zero overtone number, namely, this specific subset, right? If you try to do what I said, vary the mass and, rotate them, you end up with something that blows up at the origin. Okay. And if you take those into account and plug in the formula for the CH in our paper, then you get something. And then if you take that into account, take a difference like this, and then you exactly reproduce what you expect from a solar torus result. Okay. Yeah, and in fact, we actually did the same analysis for massive higher spin on selectivity, and also a master vector on Narii. Yeah, but it's all consistent. Yeah, and one comment is for vector fields, it is always found that the ZH takes the form of a partition function for a scalar on the codimension 2 sphere, okay. Which sort of justify the name H, right? Because the codimensional sphere is like the bifurcation surface, right? And for general S, the CH will receive contributions from spin 0 all the way up to spin S minus 1, depending on codimensional sphere. Yeah. Right. And well, actually, time is up. But any questions so far? Here, yeah. Okay. I won't have time to explain everything, but here, okay. So what we did so far is, we argue that the path integral, right, can be written as a ratio of some bulk and edge partition functions, right? And the first part of the talk explained the canonical interpretation of the bulk part, right, in terms of traces. So we can ask the same question for the ZH, right? And we think of that as some kind of thermal trace, for some Hamiltonian, right? Does it, correspond to some contribution from some kind of edge sector, blah, 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 yeah. And back to the Lorentz nature, how do we find these modes and how do we quantize them, everything, right? It's a natural question. So yeah, and sorry, and also this ZH seems related to edge modes, discussed by a lot of people in the context of the entanglement of gauge theories or gravity. Yeah, so it turns out that well, for these questions, there's an ongoing work, but the answer is yes for Maxwell at least, and we're writing this up, about that. So yeah, these slides just try to explain how we find these edge modes and how to compute this further, but maybe we'll discuss that later. Anyway, yeah, so the summary is that, again, for any free quantum field theories on a Michael background, we find that the Euclidean partition function is form. Okay. And here, this field C bulk is a sort of renormalized thermal canonical partition function, which should be understood as a formal ratio like this. Okay. And explicitly in the formulas, it takes a form of integral, some polynomial character. And the CH only exists for spin higher than or equal to 1, and is related to a specific subset of polynomial modes that fail to regular to some regular Euclidean modes. Okay. And for the case of Maxwell, we indeed found a canonical interpretation for the edge part. Okay. In terms of some kind of edge modes living on the horizon. So yeah, the last two remarks is that the picture of scattering from the horizon, back to the horizon, so suggests there might be some formulation even for interacting theories, and I think it would be interesting to think about that. And for the edge mode story, it's work in progress. We're thinking about gravity as well, and so yeah, that's all I want to say.